Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant and prepare for the future. I spoke a few videos ago about the idea of recovering components from old devices, and I realized that on this channel I never presented a tool with which to be able to test capacitors. Whenever we are recovering capacitors, especially electrolytic capacitors from older devices, we have to basically ask ourselves if those capacitors are still good enough for us to use them, or if they are just completely broken. If we are talking about electrolytic capacitors, the electrolyte inside can evaporate, can dry, and the capacitor is no longer good. Similar things might happen to other types of capacitors, so overall it's a good idea to, and actually I would say it's mandatory, to test each and every capacitor we recover from an older device, and to just throw away whatever capacitor is not good enough anymore. I created a circuit and I presented it on my other channel in my language more than a year ago, and I completely forgot that I haven't presented it here. So this is what I'm doing with this video. Now, my idea is not really my idea per se. I realized that this is a problem more by watching Mr. Carlson. Some of you might know him. Who doesn't? Now you found out about him. Mr. Carlson's Lab, it's a YouTube channel made by a guy, Paul Carlson, who is very, very knowledgeable. I do recommend you search for his channel. You can learn a lot from him. I also became a Patreon, and I'm basically now having access to all sorts of schematics of devices that he designed. And my design, or rather the need and the idea of me building the circuit that I'm gonna show you in this video of mine, was heavily inspired by his own low voltage capacitor leakage tester. Now take low voltage with a grain of salt. I will explain in a bit. I will give you a bit more details as to why I haven't built his version of this capacitor leakage tester, but I built a different one, my own version. Now let me quickly explain to you the problem before we actually move forward, and I show you the schematic that I present to you, and then we go to the workbench and we actually test some real-life capacitors just to see how my device works. My device is that I'm presenting to you is just a circuit made on a breadboard, because I already have my device built, so now I've just made it on a breadboard just for you. But nevertheless, I will show you how he works. Now, what the problem is? Well, as we know, or if we don't know, we are learning now, a capacitor doesn't have only capacitance. It also has a bit of inductance, a bit of resistance, and that's the problem. We have two different kinds of resistances. And these resistances tend to, or might be, changing value over time. So we have what's called an equivalent series inductance, SLU, an equivalent series resistance, SRU. Just like their name implies, they are manifesting those inductances and resistances in series with the capacitor. There are actually devices or circuits that you can find on the internet that are capable of measuring the SRU of a capacitor. That's separate from the actual capacitance of a capacitor that can be measured nowadays with almost all multimeters. But besides these, the capacitor in time might develop what some people call a leakage resistance, or what I like to say equivalent parallel resistance, and I've heard Mr. Carlson use this term as well. So I prefer using this term rather than leakage resistance, but the idea is the same. The capacitor, when it ages, it seems to have something like a resistor or a resistance connected in parallel with him, so that when you charge him up to a certain voltage and then you decouple him from that source of voltage, the capacitor starts to discharge himself, sometimes really quickly, which is not normal. Normally, an ideal capacitor should keep his charge indefinitely, okay? Of course, in real life, we don't have real ideal capacitors. We have real capacitors which have all sorts of these kinds of problems. But anyway, this is what we want to basically detect. If this resistance is too high or it's still acceptable. Because this resistance exists pretty much for all capacitors, but when it becomes too high, the capacitor is no longer fit for service, so to speak. We won't be able to measure the actual resistance in ohms, but we don't care that much. All we care is to be able to tell if the capacitor is in perfect shape, not perfect, but it's still good enough, or it's not good and needs to be thrown to the garbage. Now, before we move next to the schematic that I'm presenting to you, please allow me to give many thanks to the sponsor of this video, PCBWay. They are a leading PCB manufacturer with PCB manufacturing capabilities, PCB plus assembly capabilities. They can help build even your most difficult projects. You can easily get an instant quote for PCB manufacturing from the website's front page, upload the Gerber files and have your PCBs created in just 24 hours. If you need more for your project finished, they can offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. This way you don't have to do the tedious work yourself. Or perhaps if you do want to do the work, you can just order the assembled stencils. You can just finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project to offer you one-on-one customer service to make sure that your circuits get fabricated just the way you want. Are you building a circuit for a device that will need a case in the end? Then they can certainly help you with that as well, offering you 3D printing or injection molding services to have your custom-made plastic case, or perhaps CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com, the link is in the description. Thank you PCBWay for sponsoring this video, and now let's get started with the circuit that I would like to present to you. So, like I said, the problem is this particular leakage resistance or equivalent parallel resistance. So please make sure that you understand that this is not the equivalent series resistance like some people think. Therefore, it cannot be measured or detected with SR meters, with device that measure the SR. Also, this leakage resistance will not make a multimeter that is capable of measuring capacitances measure a different value of capacitance in the way that alone will tell you if the capacitor is still good enough. So if you're taking an LCR meter, for example, or any multimeter that is able to measure capacitors, and you are testing the capacitance of a bad capacitor, you might actually see a higher value than the nominal one, or at least you know, a value that's relatively close to what it should be, and therefore you won't be able to truly say if that capacitor is good enough. You actually have to charge that capacitor, and then with a very high impedance voltmeter, you need to watch what happens with the voltage across that capacitor. And here's the circuit that I am recommending to you. It's essentially a constant current source that has two different currents that we can switch by just pressing a push button, and a very high impedance op-amp set as a buffer that takes the voltage from the capacitor and spits it out towards a voltmeter. And by us watching that voltmeter, we are basically able to determine what happens and therefore draw some conclusions. Now, let me backtrack a little bit and mention the low voltage capacitor tester of capacitor leakage tester of Mr. Carson. There are two reasons why I didn't build his design. One of the reasons was that I tried and failed, and I just couldn't. Well, there are three reasons actually now that I think about it. Well, the first reason is that I tried and I failed, and I just couldn't understand what exactly I failed. I understood almost completely his schematic. Again, since his schematic is private only on Patreon, sadly I cannot show that schematic to you, but anyway, what he was doing in that device of his is basically to charge a capacitor with a relatively small current and essentially wait until that capacitor gets full. And if that capacitor would get full in a reasonable amount of time, he would basically monitor the voltage across that capacitor, or the state of charge through a VU-meter with some LEDs, I believe 10 LEDs or so. And he would basically be able to tell if that capacitor is good, because that capacitor has eventually reached maximum voltage. For some reason, I wasn't able to reproduce his design and to make it work, but that didn't bother me too much, because there was a second reason why I wouldn't want to use his design. He says that it's a low voltage capacitor leakage tester, and yeah, relatively speaking, it is. For example, in this image that I've posted now on the screen from his video, he has his own tester on the right and a larger, very old heat kit capacitor tester on the left that you were able to basically buy from the market, at least in America, I don't know, many years ago, in the 1960s, 70s, I don't know when these were made. Anyway, but those were made mostly for, at least from what I understand, those were made mostly for very old capacitors that were working in vacuum tube circuits, so they were high voltage capacitors. Okay, capacitors that were designed to work with hundreds of volts, whereas nowadays we work with lower voltage components in general. However, what he designed was basically a capacitor leakage tester that is powered by 27 volts. Yes, 27 is much lower voltage than hundreds of volts, but it's still too high in my opinion. I had plenty of recovered capacitors that were 10 volts, 12, 15. Actually, I don't know if 12, because I don't think 12 is a standard value, but I had plenty of 10 volt capacitors, 16 volt capacitors, 25 volt capacitors. So yeah, and I also have 6.3 volt capacitors, and actually if you start to recover capacitors from motherboards, from computers, and maybe other devices like that as well, you're going to find quite a lot of 6.3 volt capacitors, because they are being used on 5 volt rails, power rails, so they don't need to be higher than that. So I needed a capacitor leakage tester that can work with 5 volts, and so I can test even 6.3 volts capacitors. Okay, that was the second reason that drove me to design my own. The third reason was the fact that I didn't exactly liked his approach to injecting a small current and then being patient enough to have that capacitor charge. The bigger the capacitance, the more the time that you have to wait. I have a problem with patience. I mean, I can be very patient when I want to, but I didn't saw the logic in just having to wait so much time just to test a single capacitors. What if I have a few tens of them? I'm gonna waste an entire day. So I wanted to do things in reverse. Instead of injecting a small current and waiting the capacitor to charge, I would rather inject a high current, well, relatively high current that will make the capacitor full quite quickly, and then switch back to a very small current, almost nothing, and basically monitor what happens with the voltage afterwards. In other words, I'm watching the voltage go down from what the capacitor has been charged, rather than wait and watch the voltage go up, you know. So this is what I have right here. The circuit is pretty simple. I have a constant current source, so I'm powering everything from 5 volts, okay, which makes it very easy because you can just use a phone or a tablet charger that you don't need anymore. I have a constant current source, essentially. This transistor, these 2 resistors, these 2 diodes, these form basically a constant current source. I'm not gonna go too deep into the inner working. I'm just gonna say that quickly that this works basically by establishing a few voltages that are pretty constant. So we have these 2 diodes in series with the root 3 resistor, which are connected to the entire power rail, right? So we have here basically a constant current that flows through the diodes, which will make them have a more or less constant voltage across them, and these 2 constant voltages are being mirrored by the emitter base junction of the transistor and the voltage on resistor 1 here, or 1 in parallel with 2 if we push this button, but anyway, the equivalent resistance here. So if we have the base emitter, the emitter base junction voltage is also quite constant. So if we have 3 out of 4 voltages here that are constant, automatically this voltage on this resistance here will also be constant. And when we have a constant voltage across a constant resistance, then we also have a constant current flowing through that resistance. And we can never have a bigger or a smaller current. Well, a smaller current we could have, but a bigger current never, because then it would basically violate what's called the Kirchhoff voltage law here in this area. But this constant current that flows through this resistance is the same that flows through the transistor. It enters emitter and exits the collector, and it goes down towards the ground where we have our test capacitor. Okay, so this is how the constant current works, and this is why we can inject a constant current into whatever we would have here. In our case, we have the capacitor that we want to test. So when we are, this is a push and release button, basically. It only makes short circuit when we push down on him, and it becomes open circuit when we take our finger off of him. When we don't push the button, we only have this high resistance here, 2.2 megohms, which will make this constant current deliver less than a microamp I measured about 400 nanoamps, but you know, my devices are not so good at measuring such small currents. Anyway, it's a really small current flowing through here that basically doesn't really matters. When we are pushing this button, on the other hand, we are short-circuiting a 10 ohm in parallel with 2.2 megohms, which will become irrelevant. So we will increase this current to almost 50 milliamps. When we are injecting 50 milliamps into our capacitor, whatever the capacitor may be, we will be charging him pretty quickly to his maximum voltage. And then when we will take the finger off the button, the capacitor, if the capacitor is good enough, he will not discharge. And we will monitor the voltage across him with a very high impedance op-amp. I chose MCP 6002. It can be anything else like that, but MCP 6002 from Microchip has two advantages, or three. One, it's a really high impedance op-amp. According to the datasheet, 10 to the power 13 ohms. That's huge, like 10 tera ohms impedance. The second reason is it can be powered from 5 volts. Actually, it's got a limit at 5.5 volts maximum. And third reason, it's a rail-to-rail input-output op-amp. Okay, I hope I remember correctly, but yeah, rail-to-rail input-output. Okay, so it comes with two op-amps in package. We only need one. I just tied the second one to be a buffer as well. I didn't connected his positive input to anything. If you decide to actually build this circuit, I would strongly suggest that you also tie his positive input to this capacitor, even though you won't be using his output. So anyway, just pick one of these op-amps if you have more in the package, and use one as a buffer to take the voltage from the capacitor and throw it to a DC voltmeter. What happens is that when you release this button, if the capacitor is good, the voltage will hold, and this is what you will see on the voltmeter. If the capacitor is bad, the voltage will start to drop, and the faster it drops, the more the capacitor is, well, not good. The role of the D3 diode here is basically to prevent the capacitor from discharging himself through the collector base junction of the transistor and the resistor 3 here, because, yeah, electrically speaking, it would be possible for him to do that. I chose a Schottky diode just so I have a very low voltage drop on the diode, because I don't want to waste too much here. Theoretically, we could have a regular rectifying diode, but like I said, I wanted to have very small voltage drops. And that's the whole philosophy. Like, the circuit is not super complicated, and what we're doing is not rocket science, but it is good enough. So, now that I've explained how this works, let's go to the workbench, where we will spend quite a bit of time testing some capacitors, just so I can give you a few examples and so you can see clearly how one behaves and how another behaves. Alright, so let me turn this on. Okay, so what we have here, like I said, the circuit on the breadboard, because I already built a version of the circuit separately for myself. I'm just presenting it to you, and the voltmeter with which I measure the output voltage. I'm powering this from 5 volts from a power supply outside of this screen. And I have a push button here. See, if I push him, it goes up to almost 5 volts. And 2 wires here for me to attach capacitors. If I don't attach capacitors, the circuit is very sensitive, so I get all sorts of in-between readings. So let's start by basically making a reference, if I could call it like that, a reference measurement just for us to see how a good capacitor works. So I have here, let me, okay. 1 microfarad, come on, focus. 1 microfarad, 100 volt capacitor. Okay, I don't know the brand. Maybe you guys can recognize this 2K thing. I don't recognize the brand, but I can definitely tell you that it's new. I mean, I bought it I don't know, a year or 2 years ago, but it's still new. It's still good, and it's cheap. Like, that much I can tell you. I haven't bothered paying a lot of money on good capacitors, on really good capacitors, because I don't, at this point in time, I don't see much point. Anyway, do be careful about the polarity of polarized capacitors, right, when you insert it into the circuit. So I will connect him, and he is charging. He can charge pretty fast because it's just 1 microfarad, but like I said, we push down this button, it gets charged to the maximum potential voltage, and then we release the hand from the button. The circuit switches from 50 milliamps to less than a microamp, and we're monitoring the voltage, and the voltage should, if the capacitor is in absolute perfect shape, the voltage should remain above 4 volts if it's in absolute perfect shape. If it's in good shape but not perfect, it should be somewhere between 3.9 and above. And generally what drops below 3.9 volts, it's a bit of a question mark or downright bad capacitor. Okay, the voltage does drop. I mean, after all, we are applying a load. The input impedance of this op-amp does work as a load for this capacitor. However, the load is so small that the drop will be tiny, and overall the voltage will be able to be held. Now, sometimes it depends, if you have high capacity capacitors, you will have to wait a little bit more because the voltage drop will be slower, you know, just naturally. The smaller the capacitor, sorry, I hit the microphone by mistake. The smaller the capacitor, the faster it will stabilize, and if there are problems, the faster the voltage will drop. Okay, so as you can see, the voltage here is almost completely constant. I've been talking for quite a few minutes now, so I will decouple this perfect shape capacitor. Okay, I will short circuit it, so I discharge him. I will put for reference, I will put a 100 nanofarad 100 volt. Looks to be EPCOS capacitor, which is good. Polystyrene, I believe, but I'm not 100% sure. It's not ceramic, that's for sure. It's all either polystyrene or polyester. Anyhow, again, he gets charged up to the maximum pretty quickly, and of course we can press the button. Okay, if we want to, we can even short circuit just to drop the voltage. Okay, there's absolutely no problem for the circuit, and when we release the short circuit, because the capacitance is small, even at less than a microamp, he will charge pretty quickly, and we see again the voltage that is pretty good for this circuit, 4.2 volts. Okay, so these were two good shaped capacitors. Now let me show you some capacitors that are meh, more or less. So I've showed I think it was in the last video, but I'm not 100% sure. Recently I've made a video about recovering components from old devices. In my case it was a computer motherboard, and among other things I recovered some of the motherboard's capacitors, electrolytic capacitors. Okay, so we have a 270 microfarads here, 16 volts. Let me see if I can find something else. I was thinking about, yeah, okay, I'm gonna choose another one. 560, come on, focus, 560 microfarads, 6.3 volts. Okay, so this is a good choice. This is what I've tested with my tester, and I would say it's still good. It's not acceptable, it's more than acceptable, it's still good. Okay, so let's connect him to the circuit and run tests here so that you see. Okay, we press the button, 4.8 volts, we release the button. It is absolutely normal to drop from 4.8 to 4 point something. It drops pretty slow because it's a 500 microfarad capacitor, so again, this is also normal. But if we are patient enough, we need to see where this goes. At some point the voltage should stabilize, should drop less and less and less, and at some point the voltage should stabilize and not drop at all, or drop 1 millivolt every, I don't know, several seconds or maybe even minutes. Yeah, I'm not gonna speed this, I'm not gonna do post-processing on this video, so you're gonna just have to accept that you will have to be patient with this video, with me showing these things, or you can just skip ahead a few seconds, or even better, switch to high speed in the player, in the YouTube player. In the bottom right corner you have various options, including the playback speed. You can definitely make it faster, because I'm not very good with English, so I speak slower than other people, and this way you could just run through a lot faster through this video and through this part of me showing you various capacitors. Since you're gonna run these tests for your capacitors, it is useful for you to see, you know, a few of my capacitors and how the circuit behaves, just so you have a comparison, a point of reference against which to compare your results. Okay, so what we see here is that the voltage drop has slowed down, not a lot, but it's still dropping a lot less than what we saw from 4.8 to 4.3 or so. So I can tell you that this is a sign that the capacitor is still good. Okay, is still in good shape and can still be used. Again, this is a capacitor leakage tester. We're not testing the equivalent series resistance. That's an entirely different problem. We're not testing the actual capacitance of the capacitor. That's an entirely different problem. Okay, just to be sure that you still understand what's going on. And as we can see, it has kind of stabilized at this voltage. It even attempts to go up a millivolt or two occasionally. So, like I said, I think I moved something with my hands, that's why it dropped. But anyway, 4.2 volts is still good. So I'm gonna end the test here. I'm gonna short circuit this. Let me show you another capacitor taken from another 560 for 6.3 volts. Taken from the same motherboard, but one that I don't consider to be so good. So I would be very careful about how I would, or rather where exactly I would use him, in what circuits. Click 4.8. I'm releasing and the voltage drops, which is of course normal. But if I'm not mistaken, this will drop even below 4.2 volts. Like I said, this is a very valuable device that you can build for yourself if you plan to recover components from older devices, because the capacitors are most likely going to be partially broken or completely broken. Okay, and you want to be able to know this. You don't want to blindly use them in newer projects that you have. You actually want to know if you can rely on them and how much can you rely on them. Okay, 4.1 volts. It wouldn't be bad, but it's definitely worse than the previous one, that's for sure. And if it keeps dropping even more, then I will show you some really bad capacitors next, so you get to see how those look like. I was amazed when I tested my old capacitors that I've recovered. I've had all sorts of components recovered from when I was a teenager, and you know, I don't mean to bore you with my story, but as we wait for the voltage to drop a little bit more, my story is something like this. I was very passionate about electronics in my childhood and teenagehood. Then, roughly at the age of 15, 16, at the age of 16, I switched to computers. I got my first computer, and I just dropped electronics because it was too difficult back then, too expensive for me. But at that point in time, which was 20 years ago or even more, because now I have 37 years. At that point in time, I managed to recover all sorts of components from all sorts of devices that were old even back then. They were, you know, built in the 80s or so, or the 90s, but some of them were built in the 80s. So now, last year, I tested the capacitors that I recovered 20 years ago from devices that were already old. And some of them were amazingly bad, like amazingly bad. They were not holding anything anymore. Okay, so now, as you can see, this is still dropping. It's okay, it's still dropping. It's not dropping so quickly, but you know, from 4 point something volts we went down to 3.8. We'll probably go down even further. So this is a good example of a capacitor that's not, it's not quite completely broken, but care should be taken when we use this. Honestly, I would use such capacitors for small and medium power supplies. And even then I would measure the ripple voltage with an oscilloscope for the current that I want to draw from that power supply. So I would only use these recovered capacitors as the so-called bulk capacitors in linear power supplies. Really, I wouldn't put these in switch mode power supplies. Or maybe I would put them, but as an extra filter at the end. Anyhow, this is an example of a capacitor that is a bit with a question mark, okay? I'm gonna stop the experiment here. I think you understood what I wanted to show to you. Now let's take a look at some really old capacitors that are kind of problematic. So, Tesla capacitor, 470 microfarads, 40 volts. Not Tesla of Elon Musk, Tesla from, I believe, Czechoslovakia, the old Tesla. Right, so we're gonna charge him and then allow him to discharge. And I do believe he discharges even faster than the previous capacitor. Okay. Everything that I'm showing you from now on are bad capacitors that I would never ever use anywhere else. I have a box of them, a very special box of bad capacitors that I keep just for the sake of having a reference point for these kinds of tests and these kinds of videos. You know, I would never use these capacitors anywhere. Right, so he quickly dropped to 3.6. It's gonna drop even lower than that. This is just a bad capacitor. It's there's just no way that no way that it makes sense for this to be used. Okay. Okay, next one. Let's see. I'm gonna pick a few of them sort of by random. This is a Romanian capacitor. I do not know if this might not be an electrolytic one. It's old that most of the inscriptions got erased. I don't care. I'm just gonna connect him and then push the button. And yeah, I've had some surprises with some of these capacitors that are not electrolytics. Some of them kind of resurrected themselves by the virtue of just me testing them a few times, but I don't know, I would avoid using them. Okay, so this is a good example of a capacitor that I put him in that box of bad capacitors because the first and second time he tested badly, really badly. But it's the kind of capacitor that kind of recovered himself. I don't know if this is a thing. I just choose to not use him. Let's see. Let's take something else. Let's take Russian, I believe, electrolytic capacitor. I'm not sure. It might not be 250 nanofarads because it's 0.25 micro. 250 nanofarads at 500 volts. Actually, this might not be electrolytic because electrolytics, I don't think electrolytics go up to that voltage. But it doesn't matter because, well, okay, this might be also one of those capacitors that seem to be recovering after a while. Anyhow, moving on, let's test an electrolytic capacitor. This one truly is, because, you know, we have the plus sign here. It's also Russian, 200 microfarads, 10 volts. This is definitely electrolytic. We have a marking for the positive end, so we need to be careful about that. And I'm charging him, and now he is discharging. Yeah. Like an airplane that's been shut down. He is discharging beyond any reasonable limit. Let me charge him back up, 4.8 volts. I'm taking the finger from the button, and yeah, just most likely electrolyte is completely dried. If you see a capacitor that drops down so quickly from 4.8, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 15. Like, if you see a capacitor drop down so quickly to 3 volts, it's definitely bad. Right, and I think I'm going to do just one more. Which one? Let's take a smaller one, a different manufacturing, 150 microfarads, 6 volts, also with positive marking. So click, 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 charged, and right, as soon as I just take the finger of the button, it instantly drops to 2 volts. Okay, so I'm pressing the button 4.8, I'm releasing the button 2.2, and then starts to drop. This is a completely bad capacitor. Like I said, you are highly encouraged to just throw away to the trash these capacitors, because you might mistake them in the future. I am keeping a few of them just for the sake of, you know, making these kinds of videos, demonstrative purposes, showing other people these kinds of things. So yeah, that's pretty much it. This is what I wanted to show to you. I hope you have found this to be useful. Now you know how you can test your capacitors in the future. I'm going to put the schematic back on the screen before I finish this video. I'm also going to export this to a PDF file and put it on Patreon, just in case. But you know, the schematic is very simple. You can easily draw her on a piece of paper from the screen. So, like I said, definitely a very, very, very useful piece of equipment to have. Thanks a lot for watching. Please like and subscribe to my channel if you plan to see more of my videos in the future. I am definitely moving forward towards creating more devices that will help us in the future, and more devices that we can build ourselves with as simple components as possible. This is pretty much my desire and my mission, so to speak. Although mission is a bit exaggerated, but this is my desire, and this is what I will show you on this channel. So thanks a lot for watching, and I will see you next time. Bye bye.